So when we talked about circulation on a macro level, right, it was defined by this integral of a dot product, f dot dr, because we wanted to measure the parallel component of the vector field in the direction that it aligns with our parametrized curve. But then when we went to make that into a microscopic measurement of the circulation density at a single point, we took this circulation integral, we divided it by the area of the region that closed curve was bounding, and we took the limit as that area shrunk down to zero. And in that case, it turned out that the circulation density that we got was the x partial derivative of the y component of the vector field minus the y partial derivative of the x component. So it was not a dot product of the nabla, the derivative operator. It wasn't a dot product of that derivative operator with the vector field. It was the scalar cross product of this derivative operator with my vector field. So the macro level circulation was defined by a dot product. The micro level circulation density was defined by a scalar cross product. So now our question is, how does it work for flux integrals? If to get a flux integral we replace the dot product in the macro level with the scalar cross product, then to get to the micro level, we might have to replace the scalar cross product with a dot product. And so part C is just asking you to write out a formula for what would it look like to take the dot product of the derivative operator, which again is just the operator that has the partial derivative operators d by dx and d by dy as its components. If I take the dot product of that with a vector field f, whose components are f1 and f2, then the question here is just what would that formula look like? How would we compute this circulation density? And then in part D, I'm going to ask you to compute the circulation density for each of the three vector fields that were a part of the previous activity and see how those answers might provide support for the predictions that were made in that previous activity. So let's do parts C and D together. If it's true that the circulation density is given by the dot product of the derivative operator with the vector field f, then that means that that should be given by the x partial derivative of the first component of the x component added to the y partial derivative of the second component. And so this combination of derivatives is what's going to give us the flux density instead of the circulation density. So that if, for example, we look at the three vector fields that we started with in the previous example, the first vector field that we thought was shrinking area everywhere, that's this one. Because it's shrinking area everywhere, we compute that flux density and we get a negative number, a constant negative number. So everywhere in the xy plane, no matter where we go, it's shrinking area. How can we tell? Well, no matter what closed curve that I draw in the xy plane, and no matter where I place it around the xy plane, the ratio between the flux, the total flux into or out of that curve, and the area inside of my curve is always the same number. It's -2. So that if I let that area go to 0, my flux density is still just going to be that limit of the ratio of the flux to the area is just -2, no matter where in the plane that we happen to wander. And so that shrinkingness at every single place in the xy plane is conveyed by that negative value for the flux density. Similarly, for the second vector field, y comma x, we thought that it looked like it doesn't shrink or grow area anywhere, that this was our hyperbolic flow. And sure enough, every simple closed curve that I draw here on the xy plane is going to have 0 flux. And so when the area of that curve goes to 0, the ratio between flux and area is always just equal to 0. And so that flux density is 0 everywhere, no matter where in the xy plane that we wander. The interesting one of the three was this third vector field, xy comma 1 minus x, where the prediction was that it's shrinking area below the x-axis, so quadrants 3 and 4, and it's growing area above the x-axis, quadrants 1 and 2. When we find the flux density, we end up getting the function y. So where that function is positive, in other words, above the x-axis, the vector field is growing area, and where that function is negative, below the x-axis, the vector field is shrinking area. And that comports with what we got, right? That if I pick a flux that's above the y-axis, we get a positive value. A flux that's below the x-axis in this example has a negative value. And that ratio, that's what we're really looking for when we're talking about flux density. The ratio of the flux to the area is positive up here, and it's negative down there, which aligns with the expectation that we had. So this integral up here sort of walks and talks like a flux integral should. There's one caveat with this, and that's that we wanted to use a unit tangent vector rather than the regular velocity vector. So we have to divide by the magnitude of r prime to actually make it a real honest-to-goodness flux integral that has the right units and everything. But other than that, this integral looks an awful lot like a total flux, a macroscopic measurement. And also, this infinitesimal measurement, this dot product of the derivative operator with f, looks an awful lot like a flux density. And so we had Green's theorem that related these two things together in the world of circulation. And so now we need to figure out what is a corresponding version that links these two things together in the case of flux.